Welcome back to the Deep Dive. Today, we're looking at a tool that's really changed modern medicine, the endoscope. We want to turn it from, this kind of mysterious cable into something you understand, a piece of hidden engineering, really. Our goal for you is fast, but thorough knowledge. We want you to get the core components, the complex controls, and the tiny physics that make this flexible tube into a, precise working platform. We all kind of see the end result, right? A camera goes in, doctors look around, maybe fix something, no big surgery. But, you actually look at that tube, how does something so flexible also stream HD video, carry bright light, squirt water, suck stuff out, and steer precisely? Seems almost impossible.
It really is a marvel, and that's what we're diving into today. It's definitely not just a camera on a stick. It's a composite tool. It's got to handle light, sensors, multiple tiny channels for air, water, suction, instruments, all while being safe to navigate inside the body. So just to set the scene quickly, terminology-wise, we often talk about the distal tip, that's the far end, the bit doing the work inside the patient, and proximal, that's the end the operator holds. Our goal today is really to demystify the design, so by the end you sort of understand the logic, maybe feel like you could almost fly it.
Okay, sounds good. Let's unpack this machinery. Maybe trace the signal flow. Start with the main structural bits that have to work together. Where does the sort of brain power and steering actually start?
Well, it starts with the operator, obviously, their skill, but the physical control begins right at the control section. This is basically the handle, the cockpit, you could say. It's where you've got the dials for steering the tip, the valves for air, water, suction, and the buttons to capture images. It's really the main interface between the human and the machine.
Right, the handle. But that handle needs power and connections, doesn't it? Which brings us to the universal cord.
Exactly right. We often call it the lifeline. This cord connects that control section to the external support structure, the processor unit, the light source, which is incredibly bright, by the way. And what's really clever here is the design decision about weight. That cord carries the heavy stuff, the intense light fibers, air pressure lines, water supply from the outside in. So by doing that, the actual tube going inside the patient, the insertion tube, is kept much lighter and more flexible. It dramatically improves how the operator can control it, the feel of it.
Oh, that makes perfect sense. Keep the heavy lifting outside the patient. Okay, and then the star of the show, the bit that actually travels inside, the insertion tube. It's not just a simple hose. What are the key sort of internal highways packed inside this thing? It has to carry light, suck fluid, inject air, let tools pass through, all at the same time. What makes that long, flexible part so much more than just, a tube?
Yeah, that's where the real engineering magic happens. On the outside, you see a smooth, slick plastic jacket, right, designed to glide easily. But underneath that jacket, the tube is built up in layers, almost like a complex armored cable. And these layers have to manage three, often conflicting, demands all at once. First, resistance. It absolutely must resist kinking or getting crushed inside the body. Second, flexibility. It has to bend smoothly and predictably. You need to know where it's going. And third, this is the real secret sauce. It has to allow for reliable torque transmission.
Torque transmission. Okay, that sounds challenging. Trying to carry a twisting force accurately over something long and flexible, so I have to twist the handle just a little.
You need that exact twist to happen at the tip, maybe quite far away, precisely. Yes, it's a phenomenal challenge. And the solution is actually borrowed from mechanical engineering. Think about a flexible drive shaft or maybe a high-quality bike brake cable. Inside the endoscope tube, engineers use layers of fine steel braiding and spiral metal bands. This internal structure ensures that when the operator rotates the handle, that twisting force travels reliably and proportionally right down to the distal tip. This is absolutely vital. Without accurate torque transmission, the whole thing would just be an uncontrollable, floppy noodle, basically. It's what turns it from a wet noodle into a steerable instrument.
Now, that bike cable analogy really clicks. It shows how much hidden structure is needed just to handle rotation properly.
Yeah.
Okay, so let's switch from the structure to how you actually use it, the operational controls. Most scopes use those color-coded buttons, right? Let's start with the one that sounds a bit tricky. The blue button. It does both air and water. Why combine them?
Yeah, it seems odd at first, but it's really about efficiency and speed during a procedure. The operator needs to maintain the view constantly. So a light press on that blue button sends air that's called insufflation. It gently puffs up a hollow organ, like the colon, opens up the space so you can see better, especially around corners. But if they press that same button firmly, it instantly switches. Now it sends a little jet of water through a tiny nozzle right onto the camera lens to rinse it off. You need air pretty much constantly to keep the space open, and you need to clear the lens the instant it gets dirty. Combining them means super fast switching with minimal hand movement.
Okay, that makes sense. Prioritizing keeping the view clear quickly. And the red button is simpler. Just suction.
Exactly. Simple function, crucial job. Removing liquid, debris, whatever is obscuring the view.
And the steering
Oh,
itself.
oh.
That's done with the two dials on the control section.
Okay.
Very sensitive, like a good game controller, really. One controls up-down movement of the tip, the other controls left-right. Allows for those fine, deliberate adjustments. Okay, now let's get into the internal plumbing. This part I found really counterintuitive in the notes. It says the suction path and the accessory channel, like for biopsy tools, share the same route. Wait, the tool channel and the suction tube are the same pipe? Doesn't that mean you're constantly risking a clog from the tool itself?
It does sound risky, doesn't it? But it's actually a very intentional and quite clever design trade-off. They share the path primarily to save space inside that already crowded insertion tube. Every millimeter counts. This shared channel lets the operator quickly switch between clearing fluid with suction and then passing an instrument like biopsy forceps or maybe a snare for a polyp. And here's a really neat part. This shared route acts as a built-in troubleshooting guide. If the suction suddenly gets weak, the very first thing they check is the accessory port, because 9 times out of 10, the cause is a subtle kink or a bit of blockage from the instrument or some debris in that shared channel. Clear the channel, and bam, suction is back to full power.
Huh. That's actually pretty smart, turning a limitation, lack of space, into a functional diagnostic feature. Okay, but the high-flow washing system, that's different, right? That's separate.
Correct. The powerful water jet, the one used for really washing the area or pushing away stubborn debris, that travels in its own dedicated larger channel. And crucially, that powerful jet is usually activated by a foot pedal.
A foot pedal. Why?
It keeps the operator's hands completely free. They're already busy steering the tip, maybe manipulating a tool through the accessory channel. Adding another hand control would be too much. Foot pedal makes it manageable.
Right, okay. Hands are busy. Makes sense. Okay, moving on to actually seeing. Once the path is clear, the lens is clean, how do they get such good images? The camera chip must be incredibly tiny, and the light has traveled quite a distance.
Yeah, the basic image capture relies on a tiny sensor, usually a CCD or a similar chip right at the distal tip. It converts the light, which has traveled down hundreds of very fine, fragile light guide fibers, into electrical signals. That's the baseline. But the real cleverness now comes in the image enhancements designed to spot things that are really subtle early signs of problems. Modern scopes typically use 2 main approaches to enhance the view, helping clinicians see things they might otherwise miss. One approach is basically computational. It's called digital chromoendoscopy. This is all done by software in the processor unit. It digitally manipulates the color spectrum and contrast of the image after it's captured. This can highlight specific patterns in the tissue lining, the mucosa, or changes in blood vessels. It's like a sophisticated digital filter, enhancing visibility through software.
Okay, so that's a software boost. And the other method, near focus, you said that's different. That's optical.
Exactly. Near focus isn't software. It's a physical change in the optics at the very tip of the scope. It's a mechanical adjustment. Activating near focus literally shifts the lens elements to bring objects that are very, very close into sharp focus. This lets the operator see extremely fine details, like subtle textures or tiny irregularities on the surface that would be blurred or missed when the scope is focused further away. It's like switching to a macro lens on a camera, but happening right at the scope tip.
So one's a software filter, the other is like physically changing the lens setup.
Got it. Okay, finally, let's touch on some specialized physical features for specific challenges. You mentioned variable stiffness and the tip elevator. These sound like very targeted solutions. Let's start with variable stiffness. You often find this on colonoscopes, right? Why would you need a dial to make the tube firmer? Doesn't that fight against the need for flexibility? It seems counterintuitive, but it solves a really common and difficult problem called looping. Imagine pushing a long, flexible tube into a winding space like the colon. If it's too flexible over its whole length, it tends to just curl up on itself, forming a big loop inside, instead of the tip actually advancing forward. This looping can be uncomfortable, even painful for the patient, and makes it really hard for the clinician to reach the target area. So the variable stiffness dial lets the operator selectively stiffen the proximal section of the tube, the part closer to their hand, after it's already been inserted away. This extra stiffness acts like a splint, preventing that big loop from forming. It helps translate the pushing force from the handle directly into forward movement of the tip. Makes the whole process safer, faster, and more comfortable.
Ah, okay. So it's selective stiffening to prevent buckling, essentially. That's clever. And the tip elevator. Used on side viewing scopes, like duodenoscopes, you said? What does that little piece do?
The tip elevator is like micro-robotics right at the end. It's a tiny hinged metal piece, almost like a little flipper, located right where the instruments come out of the accessory channel. Its job isn't steering the whole scope tip, but precisely controlling the angle of the tool as it exits the channel. Think about trying to guide a tiny wire or catheter into a very small opening, like the bile duct or pancreatic duct, which might only be a couple of millimeters wide and located off to the side. The elevator acts like a tiny adjustable ramp or lever. It lifts or lowers the emerging tool, allowing the operator to aim it with incredible precision into that tiny target. It's essential for those kinds of intricate procedures.
Wow. Okay, so when you put all of this together, the steering, the channels, the air, water section, the tools, the imaging, these special features, it really clicks. This isn't just a camera.
Absolutely not. The ultimate point is that it becomes a working platform for treatment, not just diagnosis. All those systems, the air opening up the space, the water cleaning the view in the area, the suction clearing fluids, and crucially, the accessory port allowing tools through the build in it, they all have to work together seamlessly. This synergy is what allows the operator to perform actions right there on the spot. Take biopsies, remove polyps, stop bleeding using specialized tools. The engineering translates all those complex controls and hidden mechanics into immediate, localized, often life-saving interventions, all without needing large surgical incisions. It's quite remarkable.
It really is astonishingly precise engineering when you break it down like that. Every button press, every layer in that tube, every subtle twist, it all serves a critical function. Understanding that synergy, you definitely stop seeing it as just a mysterious cable. You see it as the incredibly intricate, high-performance working platform it actually is.
Exactly. It's quiet engineering doing amazing things without much fanfare. And, as you think about this, maybe consider the physics involved, that whole concept of torque transmission we talked about, turning a simple twist at the handle into precise, reliable motion way down at the tip. Imagine the potential risk to the patient if that crucial connection failed, even slightly. That continuous, reliable link between the operator's control and the instrument's action, that's the kind of hidden engineering we depend on most when it really counts. Makes you wonder what other simple medical tools rely on similarly complex hidden physics, doesn't it?